This video is all about improper integrals. In A-level maths, we're very used to dealing with proper integrals. That's where we are integrating a continuous function over an interval where both limits are defined values. If, however, we have an integral where one of the limits is infinity, so in this first example, I'm integrating up to positive infinity. So my upper limit there is infinity. This is an improper integral. Or in this second example, I'm integrating from 0. And this function is not defined when x is 0, because I can't do 1 divided by the square root of 0. So the function is not defined at that point. So this is an improper integral. And again, the third example here, I'm integrating this 1 over x minus 2 all squared between 0 and 3. But this function here is not defined when x is 2. If I try to do 1 divided by 2 minus 2 squared, well, that's 1 divided by 0. It's not defined at x equals 2 here in the middle. So again, this is an improper integral. So an integral is improper if either limit is infinity, either the lower limit or the upper limit, or if f of x is undefined anywhere in the interval, either at one of the limits or in the middle of the interval. So that's what an improper integral is. Now, improper integrals can either be convergent or divergent. These first two are both convergent because if I were to calculate this integral, and I'll show you how to do this in a minute, I would find that the area underneath this curve converges to actually just be 1. In this second case, if I was to work out the area underneath this curve, I would find that it would converge to be 2 root 3. However, if I were to try and work out the area of the third one, well, I wouldn't be able to do it because it doesn't converge to a value. It just diverges. Hence why that is a divergent integral. So that's what an improper integral is, and the difference between a convergent and a divergent. Let's now actually have a look at how we can check, how we can actually find whether an integral converges or diverges. So we're going to do 2 examples on this slide, and then 2 other ones I think afterwards. So the first integral here, I'm integrating between 0 and 1 of 1 over x squared. Now the issue I have with this, the reason why this is an improper integral, is because the function's not defined when x is 0. You can't do 1 divided by 0 squared. So this is an improper integral, and what we're going to do is we're going to consider the limit of a value t as t tends towards 0. So I've identified what the issue with the limit is, and instead of actually trying to use 0, which I know I can't do because my function is not defined at that point, instead I'm using a dummy variable t, and I'm going to investigate what happens as t tends towards 0. So basically I'm taking that lower limit of 0, which is an issue, and I'm replacing it with this. I still want to integrate 1 over x squared. So we know that's going to integrate to be minus x to the power minus 1, or just minus 1 over x. My upper limit is 1, my lower limit is t. substituting in my upper limit and my lower limit now. So when I substitute 1 in, I get minus 1 over 1, which is just 1. Minus, substituting my lower limit in now, so minus 1 over t. Simplifying, I get minus 1 plus 1 over t. Now let's apply this limit. Let's look at what would happen if I tried to take the limit as t tends towards 0. Well, if I tried to do that, if I made t tend towards 0, 1 over t is going to tend towards infinity in the limit as t tends towards 0. Therefore, this diverges. So this is a divergent improper integral. Right, let's have a look at the second example now. So let's look at this. We've got the integral between 0 and 2 of x divided by square root of 4 minus x squared with respect to x. The issue with the limit in this case is the 2. Because if I tried to substitute 2 into this function, I would have 4 minus 2 squared, so 4 minus 4, which would be 0. And obviously I can't divide by 0, so my function there is not defined when x is 2. So to overcome that, I'm going to work out the integral from 0 to t in the limit as t tends towards 2. So I'm just taking the limit that's the issue and replacing it with t, and I'm going to consider what happens in that limit. Now, in order to integrate this, I'm first going to rewrite it as x times 4 minus x squared to the power of minus 1/2. Now, I can spot a derivative here. The inside function here is 4 minus x squared. The derivative of that is minus 2x, which I've kind of got at the front here. If I had a minus 2 here at the front, then this is the derivative of this. Obviously, I can't just randomly introduce that minus half there. That minus 2, sorry. I would have to also have a minus 1/2 on the outside of the integral to counterbalance that. But the good thing is, by doing that, I have now got the derivative on the outside here. So that means I can ignore that by the reverse chain rule and raise the power and divide by the new power. So I will get the limit as t tends towards 2 of the minus 1/2. So I'll have 4 minus x squared. I'm adding 1 to the power. So the minus 1/2 now becomes a plus 1/2. Dividing by the new power, I get 2. So I've integrated that. We're now going to substitute the limits in. So substituting the t in, I've got 4 minus t squared to the power of 1/2 minus 2 times 4 minus 0 squared, like that. Now, in the limit as t tends towards 2, in this case, as t tends towards 2, this 4 minus t squared, that's just going to tend towards 0 as t tends towards 2. Therefore, that limit converges. It converges to an actual number, 0, as opposed to in the previous example where it diverged to infinity. So this is an example of a convergent integral. So let's apply that limit now then. So like I say, applying this limit to this term here will just give me 0. So I've still got the minus a half on the outside. This first term just is 0. And then over here I've got the minus 2 times 4 to the power of a half. So that's all going to simplify nicely to be 2. So this improper integral here, it converges to 2. Next example. Now notice with this example, we've actually got two issues. We've got an issue with both of these limits. We've got a negative infinity and a positive infinity. And we're going to have to deal with these separately. So what we're going to do is we're going to split this into two separate integrals. I'm going to consider this as being the integral from negative infinity to some value. It doesn't actually matter which you pick. I could pick 3. And then also add the integral from 3 up to infinity. It's going to give the same result. I could do that, but that's not going to be the simplest way of doing it. It'll be much simpler if I pick 0. If I integrate from minus infinity up to 0, and then from 0 up to infinity, that's going to be the same as integrating from minus infinity up to infinity. And the calculations will be easier because I've used 0, so we're going to get much more simplification. Right, let's consider this first integral then. So this is my issue with the first integral. So let's replace that, and let's say the limit as t tends towards negative infinity of t towards 0. Let's consider this first of all, and then we'll come back and do the second integral in a moment. Now, to integrate this, I again actually notice I've got another spot the derivative here. The derivative of the inside function here, the derivative of the minus 2x, sorry, the minus x squared is minus 2x. So if I have a minus 2 at the front there, that's good because that then gives me the minus 2x, that's the derivative of that. I just need to have that minus 1/2 at the front to counterbalance that. Which is good because we can now integrate this. So we can say the limit as t tends towards negative infinity. So I can ignore the derivative at the front and just integrate the exponential like I normally would. And I know that the exponential will integrate just to be the exponential. So, substitute my limits in. E to the power of minus 0 squared will just be 1. E to the power 0 is 1. Minus e to the power minus t squared. Not forgetting minus 1/2 I should have had at the front here. Now, as t tends towards negative infinity, let's consider this limit now. As t tends towards negative infinity, well, the negative doesn't matter very much because it's going to get squared anyway. But the fact that it's e to the power minus, that's going to tend towards 0. That's going to converge. So e to the power minus t squared tends towards 0 as t tends towards negative infinity. So, applying that limit then, I can say that this is just going to become minus 1/2 times by 1. So that's just minus 1/2. So that is the answer to this first integral. Let's now do exactly the same thing with this second integral. So we are going to have the limit from 0 to t as t tends towards positive infinity of x e to the minus x squared dx. Now we've already integrated this once, so the limit as t tends towards infinity of minus 1/2 of e to the minus x squared. Substituting our limits in. So minus 1/2 of e to the minus t squared minus e to the power 0, which is 1. And as we saw before, in the limit as t tends towards negative infinity, at e to the power, in the limit as t tends towards positive infinity, e to the minus t will tend towards 0. Because of that negative power. Therefore, applying that limit here, we'll just reduce this integral to be minus 1/2 times the minus 1, which is plus 1/2. Positive 1/2. So, we have the first integral gave us negative 1/2, the second integral gave us 1/2, and so overall, after all that work, this integral converges to be 0. Which should actually make sense if I show you what it looks like. As I integrate this function from negative infinity up to positive infinity. Excuse me. It should hopefully now make sense why we got the answer 0 there. Right, one last thing for this video. I just want to show you the working out for why that first divergent improper integral I showed you on the screen, on the first screen, why that is divergent and why that doesn't have an answer. So that was the question that I gave. The integral from 0 to 3 of 1 over x minus 2 all squared. The issue, remember, was 2. This function is not defined when x is 2. So because of that, I have split this integral up to be the integral from 0 to t as t tends towards 2. Because remember, 2 was the issue. And then the integral from t to 3 as t tends towards 2. So we've still got the whole range from 0 up to 3, like we wanted in the question. But by splitting it up around that point 2 and conceiving the limit as t tends towards 2, we're able to do some calculating. So the next line here, I've just done all of the integration. So I've raised the power to be minus 2. I've integrated each of them. Then I've substituted the limit in. So I substituted the t limit in here. Then I substituted the 0 limit in here. With the second integral, I substituted the 3 limit in here and the t limit in there. And then on this last line here, I just did some simplification. And here's where the issue is. When we apply the limit as t tends towards 2 of this, or when we apply the limit as t tends towards 2 of this. In both of those cases, it tends towards 1 over 0. It diverges. So 1 over t minus 2 tends towards infinity as t tends towards 2. It diverges. Hence why this was a divergent integral. So there we go. That's what an improper integral is, and that's how we can still calculate it to see whether it converges or diverges.